All right, so now that we have seen how to make the breaker work in our circuit, let's quickly go over the properties of the breaker because that's I didn't really get into the details of that. So if you double click this, there's a few properties that are available to you. So let's say number one, single pole operation. So because this is a three-phase breaker, there are scenarios where you might want to see a single pole operation, meaning so each of the poles are operating differently. So in different studies, if you're performing perhaps a TRV study or TOV study, you may be performing a single line to ground fault condition. So you might want to use a single pole operation. Right now, we said no because we didn't need to. So at the end of the day, you just need to be aware that yeah, if you wanted to simulate per poll operation you can. Now, the second one was open possible at any current. That basically what that means is generally speaking, the breakers are set up so that they open at a zero crossing of the current. So what that means is if you look at that breaker right there, and if you're looking at the current through that breaker, and let's assume the breaker is closed, so there would be a current like this, instantaneous current would be kind of going up and down, just like that, right? So what would happen is that if you give it a signal here to open it, and let's say this is zero, zero current. Let's say this is I peak, positive I peak, and let's say this is negative I peak. So what it would do is that let's say if you give it a signal here to open, it may not open right at that point. It basically times it so that the breaker contacts open when the when the current is at zero, because then you would have less arcing. So you can do that setting as well. Open possible at any current. In my case, I just said no. If you said yes, you would notice open possible at any current. If you had said yes, then you would notice the current chopping limit disappears. You can't this particular option is you can no longer configure that. So the main point I want to make is that depending on what you're choosing here, some of these options become available or unavailable, and we'll see that over here as well. It says use pre-insertion resistance. So some of the breakers you can have a pre-insertion resistor. So what that means is if you have a breaker and then downstream of that, if you have a transformer, you may have a solar plant or a wind plant that you're energizing a transformer for. So there's a large inrush current that occurs when you close that breaker. So to reduce that large inrush current, a lot of time you may have a situation where you may have a breaker contacts, but you would have um, something like this set up for a breaker. So that resistor right there is what you can purchase or you can specify when you buy a breaker, so that it comes in a way that the pre-insertion resistance is provided, and then you can, if you had said yes to it, that I do have it, then you notice if you had no, then that particular whole menu is not available. But if you say yes, the whole menu becomes available, and then you can specify the resistance of that resistor, and then you can also specify the closing and opening of the breakers, and there's a lot of other settings that may come into handy if you're performing, let's say, a transformer energization study, and all of that needs to be configured as per the breaker specs. But I just want you to be aware that setting can also be set up if you needed to. But in our case, we had a no, and then current chopping limit, again, we talked about it, that in our case you could just kind of keep it at zero, but there is a phenomenon of current chopping that occurs if you keep your setting where the breaker can open at any current. Then you may have then you may want to look into current chopping limits as well. So you could do a three-phase view. If you press OK, you could see that if it could become three phases. If you had the single phase lines coming through, then you might want to use this particular view, but we don't need that as well. High voltage, low voltage. So you could see this breaker. It could have a different form, different graphic. Essentially, this is the way it's kind of used in the industrial or low voltage applications on single line diagrams. you would see like this. But in high voltage applications, it's kind of shown as a box. So we'll leave it at that, and then display power flow, and you just say yes. If you just say yes and you run it, you'll start to see the it will start to show the power flow across the through the breaker. Coming to breaker main data, one of the most important things is breaker open and resistance. So I use the default values here, but if you are actually performing a study, again, a TRV study or a TOV study or transformer energization studies, you might want to put the open resistance and closed resistances based on the actual breaker specs. But for, again, our purposes, it worked out okay. If you're doing IBR modeling, it's inverter-based resource Pscad model, again, you can possibly leave the default values as well. But it's only best that if you look at the actual specs of a typical breaker and use those. This was the breaker name we talked about. Again, this breaker name, this variable is that variable right there. So if I just change it to, let's say, my breaker, so now when it's going to compile, it's going to create a variable called my breaker, and it's showing that breaker as a graphic here. And you notice that this variable name is still BRK, so it should throw me an error when I try to run it, because there we go. And it's basically saying that, input parameter my breaker, because when I compiled this breaker, I created a variable called my breaker, and I was expecting to get an input of an open and close into that variable, but that variable doesn't exist. So now if I just change this to my breaker, my underscore breaker, and that should work, and you can see it's not throwing me an error anymore. So I'm just gonna go back here, internal input. So instead of using scopes, you can also start naming these here, and then it will start to give you the variables, or basically start to give you the currents through phase ABCs. It can also give you active power, reactive power through these. So sometimes, again, if you don't necessarily want to use a scope, you can assign, let's say, uh, breaker breaker phase A, uh, phase A current, something like that, right? And then what you can do is, once you compile, that signal will then become available, and then you can give that signal a name like that. And then just like how you can actually scope it out, and you can see it if you wanted to see it on a graph as to what those currents are like. So I'm just going to create, let's say, a graph just so you guys can see it. And I'm just going to rerun it. And so it kind of, so I'm going to stop the simulation and rerun it so you guys can see how some of those options can become available for you to view. So it says finish compiling now, and once it starts to run, um, first the breaker will likely be closed, or it will remain closed. So you can see it's green. It's going to remain closed for 150 seconds. And again, you could see this is now, you could see the phase A current. Um, it's so if I just zoom it out, so it's pretty much a zero at this point. Um, Once it's hit 150, you'll see like that. There we go. And then and now you could see the current in that way right there, because this is the instantaneous current. So yeah,